Okay, all right. Well, I'm happy to be here and really excited to share some science with you all that I think is super exciting. My own personal research is kind of only tangentially related to what I'm going to be talking about today, but I thought this was too cool not to share with you all, and so I'm presenting this more as a fan than someone who actually worked on this project, but hopefully you'll enjoy it. So the project we'll be talking about today is called DSHARP. That stands for the Disk Substructures at High Angular Resolution Project. And the goal of this project was to look at the material around young stars with the ALMA telescope and look in that material to see if there are any structures. And the main goal is to see if those structures can tell us anything about how and if planets are forming around these young stars. So the main motivation for this project can be summed up quite well by this image right here. So this is HL Tau. This is a young star. Hopefully you've seen this before, but if you haven't, I'm really excited to be the first one to show it to you. So in addition to being just a spectacular image of the material around a young star, it demonstrated that ALMA could produce these super high sensitivity, super high resolution images of this material, and it could reveal all of this really rich substructure that exists around these stars that we can see as these concentric rings. So, but it also opened up a lot of questions. So, you know, are these types of structures common around young stars? You know, is HL Tau special, or should we expect this to be everywhere? And then the big question is, you know, what role do planets have, if any, in creating these rings? And so in astronomy, the answer to almost every question is we need more observations. And so that led a group of astronomers from around the world to combine forces and propose to look at 20 more of these disks with ALMA at a similar sensitivity and a similar resolution. So without bearing the lead any further, here are the results of the survey, where you can see that in almost every case, we have this really rich structure that we can see most commonly as these concentric rings. So the projector stretch may be hiding some of the more subtle features, so I definitely recommend checking these out at home, where you can see them in their full glory. But it seems like the answer to whether these structures are common seems to be emphatically yes. You know, we see them in almost every case here just by eye. And so, you know, that's potentially a really exciting thing for understanding planet formation. But before I jump into trying to interpret these structures in kind of the terms of planet formation, I want to back up for a second and make sure that we're all kind of on the same page about what it is we're actually seeing when we look at these images. So backing all the way up to the formation of a star, we start with this cloud of gas and dust that collapses when it becomes too massive. So this cloud has its own net rotation, it has its own angular momentum, and so to conserve that angular momentum as it collapses, it has to spin faster and faster. And so that leaves all the material that doesn't immediately go into forming our central protostar to flatten out into this disk of material. Now, if we zoom in on a cartoon of that disk, there's a couple important things I want to point out. So the first is what our disk is made out of. So this kind of shaded region is depicting the gas. So we have kind of gas everywhere. In addition, we have small dust grains that are kind of these small dots that we say that those are coupled to the gas, and I'll say more about what that means. But basically, they have the same spatial distribution, and they have the same motions. And then we also have large dust grains that are decoupled from the gas, and those like to kind of settle into what we call the midplane of the disk right here. Also, when we move from the parts of the disk that are close to the star outward, we start with material being very hot and very dense, and it gets colder and more diffuse as you move outward. So those are going to be some important characteristics to keep in mind as we go forward here. But already you can see that there's a lot of structure in this type of disk, and we haven't even got to the images yet. So it's important that when we look at these images, we know, what we're actually probing. Are we looking at the gas? Are we looking at the small grains? Are we looking at the large grains? And in the case of everything I've shown you so far, we're really only probing this material, these large millimeter-sized grains that live right in the middle of the disk. So you have to exercise a little bit of caution when we try to interpret these structures, because they are really just structures that exist in these millimeter-sized grains, these larger grains that live here. So if we see a ring or a gap, that is really just a ring or a gap in these particles and not the gas. So understanding how these things are interrelated kind of requires us to understand how the gas and the dust interact. Okay, so returning to our gallery, the main thing that we're after is, I want to be able to look at one of these disks and say, oh, okay, there's a gap here. Can I say that there's a planet in that gap? Or, there's a ring here. Can I say that there's a planet forming in that ring? That's really what we're after. And so to answer that, we kind of have to walk through our idea of how we think planets are forming. So the story is a pretty simple one, conceptually. We start with these small grains. And basically, we just have a series of collisions that make these grains grow to larger sizes. Eventually, we make something that's big enough that it has its own gravitational pull, and it can start to bring in other rocks and other larger solid objects to make something that's like an Earth-sized planet. If it can continue to grow, it can become massive enough that it can gravitationally start to scoop up gas in the disk and form a gas giant like a Jupiter or a Saturn. So that's the pretty simple kind of first order way that we think about how planets form. And while this core accretion model is kind of the most widely accepted idea of how planets form, it has these three major flaws. The first is that once grains become large, roughly a millimeter in size, we expect that they're very quickly going to drift into the central star. And I'll talk about how that happens in a second. But if we can somehow overcome that problem, we come to our next problem, which is that centimeter-sized grains, based on what we know about dust in laboratories, we expect that those should shatter when they hit each other rather than combine to make larger objects. So that's our second problem. It's called the centimeter-sized barrier. And if we can somehow overcome that problem as well, it seems like the formation timescale to make the really large objects is too long. Basically, by the time you've made an object that's big enough to start scooping up the gas, we expect that all the gas should be gone. It should either be funneled onto the star or blown away. So, we're standing here on the planet. Our own solar system has a Jupiter. So we know that nature has solutions to these problems. So we just need to figure out what they are and include them in our models. So some potential solutions we've come up with are that perhaps these large planets can form from a different mechanism. Basically, kind of similar to the way a star is formed. If you have a part of the disk that is overmassive, it can become unstable and collapse to form a planet kind of just all at once. So that may be a viable mechanism to form gas giants, but we don't think it could work to form things like the Earth or small terrestrial planets. What's likely the case there is that we're missing something about the way that gas and dust interact. And I think this is where these new observations with the DSHARP survey can really tell us the most, we can make the most headway here and understand kind of how planets are forming based on understanding how gas and dust interact. And so that's what I want to focus on for the rest of the talk. And so to understand how these how gas and dust are interacting, we really need to understand how they're orbiting around their central star in this disk. So in this very kind of rudimentary cartoon, I'm showing something we'll call a rock orbiting around the Earth. And you can attain a really nice stable orbit if you have this nice balance between the velocity of the object and the force pulling it in. So basically, this object has some tangential motion that's constantly carrying it away from the central massive object, but gravity is pulling it in at just the right amount to kind of keep it in that arc. So if the planet were to become, if the central mass were to become larger, you'd have to move faster to attain the same balance. And if the central thing was less massive, you'd have to move slower. So hopefully that's pretty intuitive for just a rocky, single thing in orbit. The problem is that when you include gas, the situation becomes a little bit more complex. And that's mainly because gas has pressure. So as we talked about earlier, we said that close to the star, at small radii, the gas was hot and dense. So that means that the gas has a high pressure. And as you move outward, things get colder and more diffuse, and that makes the pressure drop. So at any given point in the disk, you're just going along in your orbit. The stuff that's inside, closer to the star, has a high pressure. The stuff that's outside has a lower pressure. So it's kind of like there's this push that's pushing you outward. So if you kind of account for that difference in pressure, you have this outward force that's kind of repelling against gravity. So if we return to our schematic here, we have gravity, we have the motion. Now if we include gas pressure, there's this extra force pointing outward that cancels part of the force of gravity. And so you have this effective force that's much less. So the result is that when gas is orbiting, it feels like it's orbiting a smaller object because this pressure allows it to orbit slower. Okay, and that's really the key thing in understanding how gas and dust interact. Because the small grains, I said before that those are coupled to the gas, those just flow with the gas motions. They don't really care. It's kind of like on a windy day when dust is picked up by the wind, it gets in your eyes, it's a pain, but the pebbles stay on the sidewalk. So in this case, the pebbles are larger grains. They're just trying to orbit around the star at the regular speed, but they are constantly surrounded by this material that's going slower. So they have this headwind, this drag, this aerodynamic drag that's making them slow down. And if we remember from our orbit cartoon, if you don't orbit at the right speed, gravity is going to win and you're just going to start to get pulled in. And so this is the radial drift problem with forming planets, is that once you make a large enough grain, it should just very quickly get pulled into the star. Now, the fact that we're observing these millimeter-sized grains at all means that somehow nature is preventing this from happening. And the main way that we think that this is possible is by basically saying that the assumption that this gas pressure is constantly decreasing is actually wrong, and that it could have some structures in it that create these things called dust traps. And so if instead of being a smooth curve, we have this wiggle, anytime you have a little peak like this in the gas pressure profile, you can actually use it to trap dust. So let me show you how that works. So anytime we're sloping up like this, dust is going to feel a drag and it's going to move inward. Anytime the pressure profile is moving up like this, dust is going to feel actually an acceleration and get moved outward. So if you're a dust particle, you're going to be brought in, brought in, brought in. Eventually you get to this point where if you move in any further, the gas is actually going to repel you back out. So this is a really nice way where we can bring dust in from the outer part of the disk and trap it right in this one location. And if we're able to do this, this solves basically all of our problems. We prevent the dust from moving inward. We create a nice little quiet environment where maybe these centimeter-sized grains can collide and continue to grow. And we confine the dust to a really small space, and potentially we can have it grow faster to make things like Jupiter-sized planets. So you're probably saying to yourself, well, that's cool, but you just drew a squiggle on there. Why would the gas profile actually be like that? Well, it turns out that if you just plop a Jupiter-sized planet into a disk, it can create this type of profile. But we're not out of the woods yet. Now we're in a bit of a chicken or the egg situation. If you can't make a planet without a dust trap, and you can't make a dust trap without a planet, then how do we get this process started at all? And so, maybe one way around this is that a large planet can form from this gravitational collapse scenario and then make this little dust, make this little dust trap, which then, can foster the formation of smaller planets. And then for one particular disk that was observed with ALMA, this is called AS209, which you can see here on the left. They ran a suite of tailored simulations for that object, where they found that if you just put a planet that has the mass of about 1/10 of Jupiter right in this gap here, it can not only create this outer dust ring, but also all of these inner rings that very well match the observations through this process called orbital resonances. So I'm not going to go into that, but it's just to say that if you can make one planet that's of decent size, you can create all these other dust rings that could potentially be the site of the formation of smaller planets. Okay, so I know you're all super excited. We solved all the problems, But I do kind of want to caution you a little bit. There are some other ways that we can create these rings. Planets are probably the best way that we can, or the most viable way that we can form the variety of rings that we've seen so far. But ice lines are also, ice lines are also a possibility. So those are when, where it's colder as you move out through the disk. And so there are places where things like H2O or carbon dioxide can move from the gas phase to the solid phase, and that can change the way that that dust, fragments and combines and stuff like that. And then magnetic fields can also create pressure in the disk. But I would say that these are, this is the most flexible one that we've come up with to describe what we've seen so far. So just to wrap things up, I think this is a really exciting new study that's shown us that these structures in disks are really common, and that they are often seen as these concentric rings is good evidence that planets could be the way that these millimeter-sized grains are being trapped and caught in these concentric rings. So I think this is a really exciting time because each one of these observations only took 12 minutes with ALMA. We were talking about 15 hours with Keck to observe these high redshift galaxies. So we're going to see a lot of these in the future, and hopefully, we're going to start to include gas and some information on the smaller dust grains as well to really make sure that planets are the cause of what we're seeing, and hopefully to inform our understanding of how planets form in general. So I'll go ahead and stop there and take any questions. Thanks.
15 hours is what we have to do to study reionization. Just because yours is so much closer. Sorry, I'm biased. I do reionization science, just like our first speaker. So,
yeah, so
this is
these are
freaking
like,
amazing, and I'm just jealous.
These are like 3 light years away. Or, I don't know, 30, I don't know. And yours are what?
13.2 billion?
Right, yeah, so that's
Sorry.
the trade-off.
All right, so we actually have a Twitter question, so I'm going to start with that.
Cool.
So I'm going to paraphrase a little bit. This is from Imaginary Unreal. And has this survey improved our understanding of the radial profile of protoplanetary disks?
Good question. I think indirectly, yes. Okay, so again, we're only looking at the millimeter-sized grains. We're not actually looking at the dust here. Or sorry, we're not actually looking at the gas. So we're just guessing what the gas is doing based on what these large grains are doing. Future surveys that use more than 12 minutes will be able to detect this pressure profile as a function of radius. It is a rather expensive observation to make, so it may take some time, but I think we can look forward to that in the future. Yeah.
All right, any other questions in the back corner?
Yeah, just a quick one. How do you know that the dust is 1 millimeter or whatever, so many light years away?
Right, yeah, good question. So an easy, a quick trick you can use is that if you see one of these maps on like a website or something, if you can find the wavelength that they were observing at, that basically tells you the size of the grain. And so these dust grains are weird. They're really complex. They're hard to kind of give you a quick explanation for, but kind of a quick and dirty way to think about it is that dust grains are really good at emitting light that is the exact same size as the dust grains. So there's a lot of like weird quantum mechanics that goes into that, but basically the wavelength that you're looking at is roughly the size of the grain you're probing. So if you go to longer wavelengths, like with the VLA, you're looking at bigger grains. If you go to shorter wavelengths with ALMA, you're looking at smaller grains. Yeah.
All right, other questions? All right, right here.
So with like fluid dynamics, there's laminar and turbulent flow. Similar flow profile.
Yes, yeah. So that's an excellent question. So these disks are, yeah. Okay, so the question was about like how turbulent these disks are. So, flows can be laminar, they can be these smooth flows. You can think of like when the smoke comes off a cigarette, it comes off really kind of thin and then it kind of spirals out. So that's the laminar part, and then that's the turbulent part. And so like in disks, we think that there has to be turbulence, but the degree is really unknown. you can't make the material move inward and fall onto the star. We know that happens. You can't do that without turbulence. But that match between that simulation I showed you and the observation was made by tuning the turbulence to just the right amount. And so it is a big unknown. And so hopefully with future gas observations, we can begin to understand that a little bit better. But it's a difficult measurement to make observationally. Yeah, thanks.
Does ALMA have enough tunability? Has anybody studied the distribution of grain size?
Yeah, that's the next step. So the HL tau image I showed you was actually probing smaller grains. And so that's a big thing too, is because the way that grains are trapped is also dependent on the dust grain size. And so if you have information on the dust grain size by looking at different wavelengths, that's one way you could test whether that's really how it's happening. So that's definitely in the works. But ALMA is a really oversubscribed telescope. Everyone wants the time. People that study galaxies, people that study stars.
We can use it too, yeah.
Yeah, so so everyone's after it, and so the time is really hard to get right now, but that's also one of the things that will be coming down the pipe soon.
All right, so I'm going to end on another Twitter question. This is from Rena. Are any of these stars close enough to actually detect planets?
That's a great question. So by detect, I assume that you're meaning detect them directly. So there are some planets that we can actually detect around a star. We can actually catch light from the planet, but it usually usually it's a tough measurement to make. So we can only detect really big planets, like things that are bigger than Jupiter. And so, I think what that simulation I showed shows you is that you can make these rings with really small planets, and those ones are too small for us to currently detect with the technology we have. So it's going to take the next generation of big telescopes to be able to do it. But I think these ALMA observations are giving us a good place to look.
Awesome. All right, let's thank our speaker one more time.
Thank you.